Welcome to you in the course Theory of Mechanisms and Machines. This is our first lecture, and let me start with the definition of the subject. Theory of Mechanisms and Machines is an applied science which describes the relationships between the geometry and motion of a mechanism or machine and the various forces involved in the motion. Various forces involved in the motion. So basically, the subject defines the motion of a mechanism or machine in two aspects. First one, it describes the motion as a function of geometry only, and in the second stage, it describes the various forces involved in the motion. So based on this, the subject can be divided into two groups. Number one, that is kinematics, and number two is kinetics. In kinematics, the motion of a machine or mechanism is function of geometry only. So motion is function of geometry only. And we do not consider the forces. Forces are hidden here. So we do not consider the forces in first part, that is kinematics. That doesn't mean that forces are absent. Without force, motion is impossible. But here we do not consider the forces, as forces are hidden in the first stage, that is kinematics. In second stage, that is kinetics, we consider the forces, and this subject defines the various forces involved in the motion. So in the second stage, it defines the forces involved in the motion. So this subject is broadly divided into two groups, kinematics and kinetics. Let me explain this with help of an example. Let us consider a windshield wiper mechanism of an automobile, and this is the windshield and this is the wiper blade. So to design the wiper mechanism, the designer first have to confirm that this blade can cover the desired area or not, and that depends purely on geometry of the mechanism. And second stage, he or she has to determine what is the power requirement of the motor to overcome the frictional and inertial forces. So forces comes in the second stage, that is called kinetics. So first part of the subject is kinematics, and we'll start our course with kinematics of machines. Kinematics of machines. So first part is kinematics of machines. Now let us see what is the definition of a machine. A machine is a device which transfers and transforms the motion and force or power the motion and force or power from the source means input, to the load, that is out. So a machine is a device which transfers and transforms the motion and force or power from the source, that is the input, to the load, that is the output. Let me explain this with the help of an example. So this is an IC engine where this is the crank, this is connecting rod, this is the piston, and this is the cylinder. So as a input, that is or source, gas force is available at piston. In IC engine, gas force is available at piston. So this is as input, gas force, which is as input available at piston. And the motion of the piston is to and fro rectilinear oscillation. To and fro rectilinear oscillation. So this motion is transferred to the crank by this IC engine. This is an IC engine, which is a machine. So this machine transfers the input motion which is available at piston to the crank, which is nothing but output. And motion of the crank is continuous rotation, which is continuous rotation. So this engine or machine transfers the motion from piston, that is the input, to the output, that is the crank. Not only that, it also transforms the motion, that is from to and fro rectilinear oscillation to continuous rotation. So a machine does two works. It transfers and transforms the motion and force or power from the source, that is the input is gas force here, to the load, that is the output. A load is present at the crank for IC engine. And we have to note another point also, that input is available. Input is available for us. So input is available to us. Input is available to us, whereas output is desirable to us. So the continuous rotation is desired to us. So input is available and output is desirable. Now we have seen that input in IC engine is to and fro rectilinear oscillation, whereas output is continuous rotation. There are various combination between input and output. The vice versa is also possible, that input is continuous rotation, output is to and fro rectilinear oscillation. Input is continuous rotation, output is unidirectional rectilinear motion. Vice versa of this is also possible, from unidirection rectilinear motion to continuous rotation. Now continuous rotation at different speeds, input is continuous rotation, output is also continuous rotation, but at different speeds. From continuous rotation to angular oscillation, and vice versa of this is also possible, from continuous rotation to intermittent rotation. So these are the various combination between input and output motion. That is, this is the transformation of motion. So a machine transfers and transforms the motion and force or power from the input to the output. And these are the examples of various combination between input and output motion. Now let us see what is kinematics. What is the subject kinematics? Kinematics is the subject that deals with only geometric aspect of motion without considering the forces. So in kinematics, forces are not considered. The motion is defined as a function of geometry only. So here motion is function of geometry only. And in kinematics, a machine is referred as a mechanism. In kinematics, in study of kinematics, a machine is called as a mechanism. So when we study kinematics, we call a machine as a mechanism. Now let me give you the technical definition of mechanism. Mechanism is combination of interconnected rigid bodies, which are technically called links, capable of relative motion. So this is the combination of interconnected rigid bodies. This term has a importance in mechanism. We know that a machine is called a mechanism when we study kinematics. And kinematics means geometric aspect of motion. So these links must be rigid in kinematics. Why? Because forces are present. When a machine is in running condition, various forces are present there. That forces will deform the links if they are not rigid. If they are not rigid, that forces cause deformation of the links. Then the geometric value or geometric form of the links will be changed, or geometric values will be lost. So geometric analysis will no more valid there. So links must be rigid when we study kinematics. Otherwise, geometric study will be invalid. Now let us come to one very important point, that is kinematic pair. We know that mechanisms are combination of interconnected rigid bodies. The rigid bodies are called links. Now the interconnections between links of a mechanism are called kinematic pairs. So the interconnections are called kinematic pairs. Now before going to detailed study, please note two important terms, that is degrees of freedom and pair variables. Degrees of freedom. It is the minimum number of independent coordinates. Minimum number of independent coordinates required to completely define the relative movements between links is called degrees of freedom of a kinematic pair. We know that kinematic pair connects various links, and the minimum number of independent coordinates required to define the relative movement between links is called degrees of freedom of that kinematic pair. And the independent coordinates are called pair variables. So pair variables are the independent coordinates. The independent coordinates are called pair variable. Now let us see what is degrees of freedom of an unconnected rigid body in space. Of an unconnected rigid body in space. So let me draw one Cartesian coordinate system in a space. So this is a three-dimensional Cartesian coordinate system in space, which is x, coordinates are x, y and z. An unconnected rigid body can translate along x direction by an amount delta x. It can also translate along y direction by an amount delta y. It can also translate along z direction by an amount delta z. It can rotate about x-axis by an amount delta alpha. It can rotate about y-axis about y-axis by an amount delta beta, and it can also rotate about z-axis by an amount delta gamma. So there are 6 motions available for an unconnected rigid body in space. 3 translations are delta x, delta y, delta z, and 3 rotations are delta alpha, delta beta, and delta gamma. Now, these 6 independent coordinates, that is 3 translations and 3 rotations, all these 6 coordinates are independent to each other. Why they are independent? Because we can give any amount of delta x, we can give any amount of delta y, any amount of delta z. Similarly, any amount of delta alpha, any amount of delta beta, and any amount of delta gamma. So, all these 6 independent coordinates, all these 6 coordinates are independent, as we can give any amount of value to for each coordinates. So 6 independent coordinates are required to completely specify the relative motion of an unconnected rigid body in space. So degrees of freedom of an unconnected rigid body in space is 6. So degrees of freedom of an unconnected rigid body in space is 6. Now let us see what is degrees of freedom of an unconnected rigid body in plane motion. We have discussed for space, now for plane. So define that. Let us consider xy plane. So this is x, this is y. And this is an rectangular rigid body, unconnected rigid body or free rigid body. That is A, B, C, D. This is one instant where orientation of ABCD is like that. And in second instant, the orientation becomes like this. This is A prime, this is B prime, this is C prime, this is D prime. Now let us first locate or define the position of B prime from B. That is, the x translation of point B is delta x and y translation of point B is delta y. So by these two independent coordinate, point B, motion of point B can be defined, completely defined, point B. But that doesn't ensure the relative motion of the entire rigid body. Why? Because we have located point B prime, but there may be a rotation of this face AB by an amount delta theta. So now if we define these three, that is delta x, delta y and delta theta, for any face AB, then the orientation of the entire rigid body has been defined, completely defined. So three independent coordinates are required to completely specify the relative motion of the rigid body, and they are two translations, that is delta x, delta y and one rotation, that is delta theta. And here we can give any amount of delta x, any amount of delta y and any amount of delta theta. So each of them are independent to each other. So degrees of freedom of an unconnected rigid body in plane motion is 3. So degrees of freedom is 3. Now let us classify the kinematic pairs. And first we will classify it based on nature of contact. Nature of contact. Kinematic pairs connects different links, and the contact between links, based on the contact between links, we can classify kinematic pairs under three headings. Number one, that is lower pair. Number two, higher pair. And number three is wrapping pair. In lower pair, the links are connected through their surface contact. Surface contact. So links are connected through their surface contact in lower pair. In higher pair, links are connected through their line or point contact. In wrapping pair, one body is completely wrapped around another. So in lower pair, there is surface contact between links. In higher pair, contact is made through line or point contact. And wrapping pair, one body is completely wrapped around another. Now let me explain various kinds of lower pair first. So let me show you the various kinds of lower pair. This is the first kinematic lower pair, which is called revolute. or turning pair. This is body 1 and this is body 2. Body 1 is a cylindrical rod and in body 2 a cylindrical hole of same diameter of body 1 is made, and in addition two collars are made on body 1. These are two collars which are made on body 1. So these collars are integrated part of body 1. Now if we fix body 1, then all translation motion of body 2 has been restricted. That is, body 2 cannot translate along x, cannot translate along y, as well as is cannot translate along z. Three translatory motion of body 2 has been restricted. Body 2 can only rotate about axis of body 1. This is the axis of body 1, and this rotation can be defined by delta theta. So only one rotation can completely define the relative movement between body 1 and body 2. So degrees of freedom is 1. So degrees of freedom of revolute or turning pair is 1, and pair variable is delta theta. And this axis of body 1 is also called the axis of revolute pair. This is a model of revolute kinematic pair. This is body 1, this is body 2. And inside there is a cylindrical pin, and these two are the collars, and the cylindrical pin and the collars are integrated part of body 1. Now if I fix body 1, body 2 can only rotate about the axis of the cylindrical pin, that is the axis of the revolute pair. So only one rotation is allowed in this kinematic pair. The second kinematic lower pair is prismatic pair. This is body 1 and this is body 2. Body 1 is a rectangular bar, and on body 2 the same size of rectangular slot is made. At this combination, if we fix body 1, then body 2 can only translate along the slot. All other motion of body 2 has been restricted, and this motion can be defined by a single coordinate, that is delta s. So by a single independent coordinate delta s, the motion between 1 and 2 can be described. So degrees of freedom of prismatic pair is also 1, and pair variable is delta s. So prismatic pair only allows translation along the slot. This is a model of prismatic kinematic pair. This is body 1 and this is body 2. On body 1 there is a rectangular slot, and body 2 is a rectangular bar only. Now here if we fix body 1, if we hold fixed body 1, body 2 can. The third kinematic lower pair is screw pair. Screw pair, where body 1 is a screw and body 2 is nothing but a nut. Body 2 is nut and body 1 is screw. And body 1 helical threads are made. And a screw nut pair, if we fix the screw, the nut can rotate as well as translate along this direction. So two motions are available for the nut, one translation delta x and one rotation by amount delta theta. But these two coordinates, that is delta theta and delta s, are not independent to each other. Why? Because if we make delta theta as 2 pi, delta s will always be L, that is the lead of the screw. So we can develop a relationship between delta theta and delta s, that is delta theta by delta s is 2 pi by L. So they are related to each other, they are not independent to each other. We cannot give any amount of delta s and any amount of delta theta. For a particular value of delta theta, delta s will be fixed by this relationship. So only one independent coordinate, that is delta theta or delta s, can completely specify the motion between screw and nut. So degrees of freedom of a screw pair is 1 and pair variable is delta theta or delta s. This is a screw pair, this is the screw and this is the nut. A blue point is marked on the nut. Now if I fix the screw, the nut can rotate, as well as it can translate along the screw. Now for a given amount of rotation, the translation is always fixed. Vice versa, for a given amount of translation, rotation, value of the rotation is always fixed. So only one of them, that is rotation or translation, can define the relative motion between screw and the nut. The fourth kinematic lower pair is cylindrical pair. Here body 1 is a cylindrical rod and body 2, this is body 2. On body 2, a cylindrical hole of the same diameter of body 1 is made. Now if we fix body 1 here, body 2 can translate along this direction, that is the axis of body 1, as well as it can rotate about the axis of body 1. So two motions are available for body 2, and here delta theta and delta s are independent to each other. They are not related to each other, rather they are independent to each other. We can give any amount of delta theta and any amount of delta s. So two independent coordinates are required to completely specify the motion between 1 and 2. So degrees of freedom of cylindrical pair is 2 and pair variables are delta theta and delta s. They are not related to each other, rather they are independent to each other. Say if we fix delta theta is 0, we can give any value of delta s. Similarly, if we fix delta s equal to 0, we can give any value of delta theta. So these two are independent to each other, hence the degrees of freedom is 2. This is a cylindrical pair. This is the cylindrical rod. Now here one blue point is marked on the cylindrical rod. Now this cylinder can translate as well as rotate, and this translation and rotations are independent to each other. Say for 0 rotation we can give any amount of translation. Similarly, for 0 translation, say we have fixed the translation here, we can give any amount of rotation. The fifth kinematic lower pair is planar pair. In planar pair, this is body 1 and this is body 2. If we fix body 1, then body 2 here, it can translate along two mutually perpendicular direction, that is x and y, by an amount delta x and delta y, and it can also rotate about z. This is that z axis, it can also rotate about z, like a unconnected rigid body in plane. So three independent coordinates, that is delta x, delta y and delta theta, two translation and one rotations are allowed in such pair. And all these three independent coordinates, all these coordinates are independent to each other. We can give any amount of delta x, any amount of delta y and any amount of delta theta. So degrees of freedom of planar pair is 3, and pair variables are delta x, delta y and delta theta. This is a planar pair. The fixed one, the base is the body 1 and this is body 2. Now here body 1 can translate along x direction, can translate along y direction, as well as it can rotate about z. So three motions are available here and all these three are independent to each other. The last kinematic lower pair is spheric pair. Spheric pair. This is body 1 and this is body 2. On body 2 there is a spherical ball. This is the spherical ball. And on body 1 a spherical cavity of same size is made, and body 2 is inserted into body 1. Now if we fix body 1, then all translatory motion of body 2 has been lost. That is, it cannot translate along x, it cannot translate along y, and it cannot translate along z. So it has only rotations. What are those? Let us consider this origin is O and axis of body 2 is OA. Now if we fix the angle between Z and OA by delta alpha, this is delta alpha, then this axis OA can lie on the surface of this cone. So OA can now lie anywhere on the surface of this cone. So position of OA is not completely defined. To define that, let us consider from point A we have projected point A on xy plane, and this point is P. Now we have defined the angle between OB and x-axis by an amount delta beta. By these two, that is delta alpha, this is delta alpha and delta beta, the position of OA is now fixed. But these two are not sufficient to completely specify the motion between 1 and 2. Why? Because OA, this axis OA, axis of body 2, can rotate about its own axis by an amount delta theta. So this rotation has to be considered also. That is and delta theta. These three rotations can completely specify the relative motion between 1 and 2. So degrees of freedom of a spheric pair is 3 and pair variables are delta alpha, delta beta and delta theta. This is a model of spheric pair. This steel part is the body 2 and this black one is body 1 on which spherical cavity is made, and this steel ball is inserted in the spherical cavity. So black one is body 1 and steel part is body 2. Now if I fix body 1, body 2 can only rotate, and rotations are shown in kinematic diagram, and this is the rotation about its own axis. So body 2 can rotate also about its own axis. Now let me give you the information of all 6 kinematic lower pair into a single page. For revolute and turning pair, degrees of freedom is 1. Pair variable is delta theta, only rotation is allowed, and symbol is R. For prismatic pair also degrees of freedom 1. Pair variable delta S, only translation is allowed and it is denoted by P. For screw pair degrees of freedom is 1 and pair variables are delta theta or delta S as they are related to each other. And in screw helix are made there, so it is defined by H. Cylindrical pair degrees of freedom is 2 and pair variables are delta theta and delta S, and it is symbolized by C. Planar pair degrees of freedom is 3 and pair variables are delta x, delta y and delta theta. Planar pair is denoted by G. Spheric pair also has 3 degrees of freedom, delta alpha, delta beta and delta theta. And spheric pair, symbol of spheric pair is S. So these are about 6 lower kinematic pair. Now higher pair we know when there is point or line contact between links. Examples are ball bearing, roller bearing. In ball bearing there is a point contact between ball and recess. In roller bearing there is a line contact between roller and recess. Now what is the degrees of freedom of higher pair? To understand that, I am showing only the half circle of this roller, and we are considering that the recesses are straight and we are drawing a half circle. So at instant this is the position of the half roller, and another instant it is like this. So this pair, if this is a plane motion, then this pair allows a translation by amount delta S, and it also allows a rotation by amount delta theta. Rotation of this face by an amount delta theta. Only translation along this direction, that is delta y, is restricted. So two independent coordinates, that is delta S and delta theta, can completely specify the motion between 1 and 2. If roller is 2 and this fixed surface, the recess is 1, then two independent coordinates can completely specify the motion between 1 and 2. So degrees of freedom of a higher pair is 2 and pair variables are delta S and delta theta. Next is wrapping pair. We know that when one body completely wrapped around another. The examples are belt pulley and chain sprocket. In belt pulley, the belt is completely wrapped around the pulley. Similarly, for chain sprocket, chain is completely wrapped around the sprocket. So this kind of kinematic pairs are called wrapping pairs. The kinematic pairs can be classified based on how the contact is maintained. It can be also classified that how the contact is made, and they are form closed pair and force closed pair. When the contact is maintained by geometric form only, geometric form only, then it is called form closed pair. Example is cylindrical pair. Here, if this is 1 and this is 2, the contact between 1 and 2 is made by their geometry only. So this is called a form closed pair. In force closed pair, the contact is maintained by external forces. External forces. When contact is maintained by external forces, that is called force closed pair. The spheric pair, which I have shown you earlier, the construction of such kind of spheric pair, if I repeat that, the construction of such kind of spheric pair is not possible because we cannot insert this sphere into the spherical cavity. The actual construction of a spheric pair is like this. This is body 2 and the other part is body 1, and here body 1 is made by parts. This is one part and remaining is other part, which are connected here, and between 1 and 2 there is a spring. So contact between 1 and 2 here maintained by the spring force PS, and such kind of kinematic pairs are called forced closed pair. Force closed pair. So this is the actual construction of spheric pair. So we are ending our session here. Thank you.